Alright, hello class. So in this video we're going to be extending our discussion of finding volumes using integration, and in this video we're going to be using what's called the disk method, also known as the washer method sometimes. And what this comes down to is essentially just solids of revolution. So we're going to extend what we did in the last video to apply it to very specific types of volumes, and these turn out to be a little simpler than the general slicing method we were using before. However, they are just a special case of the slicing method. Alright, so what exactly is a solid of revolution? Well, if we have a function, say here's our f of x, okay, and we say split this and just look at it from a to b like we normally would. Okay, a solid of revolution is we would take this shape and quite literally revolve it around the x-axis. Let me use a different color here. Okay, so we are essentially creating a solid by revolving this curve around the x-axis. Okay, so what ends up happening is we have a mirror image that, of course, I'm terrible at drawing, of this curve down here, and at each x we're basically creating a circle. Okay, so very much like what we looked at before, except a solid of revolution, it's pretty much always, say, a circle. So essentially a solid of revolution is when we construct a solid by revolving a curve around a line. And in this case, around the x-axis. Okay, so at each x, so here at x, we have our slice is a circle. Okay, and it's a circle with radius. Okay, so each slice is a circle with radius r equals, well, it's basically this height. All right, so that's going to be f of x at each x. So our area function, a of x, will be pi r squared, right, since it's a circle, and r is our f of x function, so it's going to be pi of our f of x all squared. Okay, so the volume ends up being the definite integral from a to b of pi times f of x all squared dx. Okay, and we got this. This just came from our general slicing method. Okay, so honestly, these are things we could actually do, but without having a special formula. But this comes up enough. These solids of revolution come up enough that it's nice to actually have the formula. Okay, so that's essentially the disk method. All right, so let's look at an example, and I'm going to start with a pretty simple one, just to see if we can actually verify, what we have, and we'll just go from there. Okay, so let's say we have this f of x here. So we want to find the volume of the solid formed by revolving this following curve around the x-axis. Well, this curve is a line, okay? And so what we're essentially doing is at each x, we're creating a circle. Okay, so if I match this on this side, let me use a different color for this. Okay, so at each x, we're basically revolving this line around the x-axis. So in other words, we're creating circles, and what ends up happening is we essentially are now creating a cone. Okay, so that's, what I want to check this against is, well, let's verify that what we get here actually matches. So for the disk method, all right, the volume is the integral from a to b of pi times f of x squared dx. Well, this is often simplified down with, say, the pi on the outside. Say pi integral from a to b of f of x all squared dx. Okay, so we need to find what f of x is. Well, here it's a line going from 0, 1 to 2, 0. Okay, so that should be, the y-intercept is 1. The slope, well, we go down 1 and over 2, so it should be minus 1/2 x. All right, so that's our function. So the volume should be pi times the integral from, well, our x's go from 0 to 2. Okay, then it'll be 1 minus 1/2 x all squared dx. Okay, and then we just crank this fellow out. Okay, so when we FOIL this out, we're going to get 1 minus, let's see, 1/2 times x minus 1/2 times x will just be minus x plus 1/4 x squared. Okay, and so we'll get pi times, now we'll integrate this, we'll get x minus 1/2 x squared plus, and then we'll get 1/12 x cubed. Okay, so we'll end up with pi. Now, we don't have to worry about plugging in the 0 because that will 0 out. So really, we're plugging in the 2. So it'll be 2 minus 1/2 times 2 squared plus 1/12 times 2 cubed. Okay, and I will put the minus 0 here just to be specific. Okay, so we're going to get 2 minus, this is 1/2 times 4, so that'll be 2. Hey, that's nice, so that cancels. Then we'll get plus 1/12 times 8. So we can take 4's out of that to get pi times, so when we take 4's out, we should get 2/3. All right, so we get 2 pi over 3. Okay, so does this actually match what we know about a cone? Okay, so what we essentially have here is a cone, okay, with height equal to, well, its height is here, that's 2, okay, and its radius is 1. Okay, let me make sure that actually looks like a 1. So if we remember what the volume of a cone is, it's 1/3 pi r squared times h. Okay, so if we put in these values into our volume, it's going to be 1/3. There we go. 1/3 pi r squared, so that'll be 1 squared, times h, which is 2, which when we simplify this comes out to be 2/3 pi, which is exactly what we got here. Okay? Well, of course, we probably wouldn't use this method just to find the volume of a cone. What we would do instead is use it for like more unwieldy shapes. Okay, so let's take a look at something like that. All right, so here we want to find the volume of the solid generated by revolving y equals 1 over x around the x-axis on the interval 1 to 2. So the reason we want to do 1 to 2 is mainly because this function blows up at 0, right? It looks something like this. But from 1 to 2, okay, it looks something like this. So what we're really looking at is this shape here. Because we're revolving around the x-axis. Okay? So here is our shape. Here's the function. You can call it either f of x or y equals 1 over x. Okay, and we pretty much have all the information we need to get this strange little shape. Its volume is going to be pi times the integral from 1 to 2 of our function squared. So it'll be 1 over x all squared dx. Okay, so this will be pi times the integral from 1 to 2 of 1 over x squared dx, also known as the integral from 1 to 2 of x to the negative 2 dx. All right, so we get pi times, let me simplify this up. Okay, so we can integrate with just the power rule, and that's why I wrote it as x to the negative 2. So it's x to the negative 1 over negative 1, evaluated from 1 to 2. Now, you might think, oh man, we introduced a negative, right? This will be negative pi times x to the negative 1 from 1 to 2, or negative pi over x, evaluated from 1 to 2. Well, what ends up happening is when we start plugging these in, let me switch to another color when we do this, we'll get negative pi over 2 minus a negative pi over 1. This is our fundamental theorem of calculus step. Okay, and what ends up happening is negative pi over 2 plus pi. So the whole thing comes out to be pi halves. Okay, so there's the volume of this odd looking shape here. All right. All right, the question that comes up now is, well, what happens if I don't want to just revolve one curve, but I want to revolve the region between two curves, right? If we have this f of x and this g of x, and I actually want to revolve this curve or this region between them, and of course I'm terrible at drawing this, but what ends up happening, and instead of revolving circles, we end up revolving little, I think of them as donuts, even though they're two-dimensional, but we end up creating this sort of hollowed out thing, right? So we've got the top part, and then we've cut out an inside part, right? That's symmetric. And this is our solid here. Right, and we have this region on the inside that's open. Okay. Well, it turns out this is what's called the washer method, which is the same thing as the disk method. Okay. And it stems from the fact that what we're actually revolving around are what you would call, say, washers. Okay, so instead of a circle with radius given by f of x for any x, now it's a washer with inner radius g of x and outer radius f of x. Okay, well, how we find that area, the area of a washer, is really just the area of the outer circle minus the area of the inner circle. Right? Because all we do is we take this big circle and we subtract away the inner circle. Okay? So it's really, at any x, it's just going to be pi outer radius squared. All right, so I'll say outer radius squared minus pi inner radius squared. Well, in this case, that's going to be, for any x, f of x squared minus pi times g of x squared. Okay, so it turns out that the volume of this, which is a terrible drawing, so maybe I should redraw it. Okay, so the volume created by generating or revolving this region around the x-axis, okay, oops, so the volume is given by, if we simplify this, we can factor out the pi. It'll be the integral from a to b of f of x squared minus g of x squared. Now, this may look familiar to you because what we're essentially doing is, once again, we're taking our top curve and our bottom curve and subtracting. Right? So this ends up being the top squared minus the bottom squared. So in the same way that we would do just the region between the curves with the top minus bottom, here we're doing a top squared minus bottom squared. And that comes from the fact that all we're doing is taking that volume generated from revolving the top guy, subtracting away the volume generated from the bottom guy to get the volume of our solid here. Okay, so let's look at an example to show sort of how this works. Okay, this example is famous. I think it's probably shown in every calculus class ever taught. So I don't want to go against tradition. So we'll do too. Okay, so what we're looking at is we want to find the volume of the solid generated when the region bounded by the curves y equals x squared and y equals the square root of x is revolved around the x-axis. So these two functions, okay, look like this, of course. So here's y equals x squared, and here's y equals the square root of x. Okay, and so the region between them Now, typically when we say that, we're looking at the smallest possible one. So really, we're looking at the region between 0 and 1. Okay, so what we'll be doing is revolving this around to get a strange looking shape. Okay, that looks kind of like this. Okay, so we've got a curvy sort of bowl shape. Okay, and it comes to a point, and then we hollow out the rest of it. Okay, so it's a strange shape that we're creating here. It's sort of almost like we take a bowl and carve a tornado out of it. Okay, that's kind of how I see it. Okay, well, to find the volume, so here's the nice thing about this. Some would argue there is no nice thing about this, but here is the nice thing about it, though. The nice thing about it is that I don't really need to know what this thing looks like to be able to find the volume. I just need to know what is the top and what is the bottom. Well, the top, and maybe I should have done it in the same color as the top, right? The top is this square root of x function, while the bottom is this y equals x squared function. Okay, and that's the reason actually this function is so famous and shows up in every calculus class I ever taught, is because this kind of operates between 0 and 1. This operates opposite of how people expect, right? Where we expect x squared to always be greater than square root of x, but between 0 and 1, it's the opposite, right? And they switch places at 1. All right, so the volume of this solid is going to be pi times the integral from 0 to 1 of, now remember it's the top squared, so the top is the square root of x squared minus the bottom squared, which will be x squared squared. So here we go, top squared, bottom squared. And of course, we subtract. All right, and then from here, it's, just an integral. Pi integral from 0 to 1 of the square root of x squared is x minus x squared squared, which will be x to the 4th. And hopefully from here, it shouldn't be anything mysterious. Okay, and we'll just do this. Plug in a 1, we'll get 1/2 minus 1/5. Plug in the 0 to get 0. Okay, so 1/2 minus 1/5, well, that'll be 5 minus 2 over 10, if we want to do that quickly. So we'll get 3/10. So 3/10 times pi will be the volume of that region. Okay. Now, another question is, well, what do we do if we want to revolve around the y-axis? Okay. So for example, let's say we want to revolve something around the y-axis instead. So say we want to revolve the region between y equals 1/4 x and y equals the cubed root of x around the y-axis. It wasn't in the actual directions here, but typically we will always want to stay in quadrant 1 when we're revolving things. Okay? So y equals 1/4 x, that's some sort of linear function like that. And then the cubed root of x, looks something like this. Okay, so we're talking about this region here between them, but we are revolving around the y. Okay, so what we want to do is revolve around the y this way. Okay, so here it looks like what we've done when we do this is similar. We have a cone that we've hollowed out a tornado shape from. Okay, but this time we are going in the y direction. So if you remember back when we were talking about regions, right, and we were talking about areas, we always did it as the right versus the left. And it was always right minus left. Well, if from what we've already ascertained that you guessed, oh, it will just be the same thing, except we will, do right squared minus left squared. If that's what you assumed, then you'd be right. Turns out the volume here is going to be pi integral from c to d of the right function squared minus the left function squared dy. Okay, so its standard definition is always like a capital F of y squared minus a capital G of y squared. Okay, so it's the same idea that we got when we were doing regions, because again, we applied the same idea when we were doing solids of revolution. So to move these things around the y-axis, all we need to do is make the integral in terms of y instead. Okay, so that's what we'll do. The right side is actually the linear function, and the left side is this cubed root function. Now, we need to get these in terms of y's. In other words, we need these as an x equals something in terms of y. Well, in this case, it's not that difficult because what we have is that x is equal to y cubed. Okay, and y here, when we move the 4 over, we get x is equal to 4y. Okay, so here in red is our left. Here in orange is our right. Okay, so now we know that this goes from y equals 0. We need to find the top piece. Okay, and to do that, we're going to see where these two guys intersect. All right, so let's do that. The intersection point, I'll put that in blue, and down here, to find that, we're going to set 4y equal to y cubed. Okay, so if we move this over, we get 0 is equal to y cubed minus 4y. Factor out a y. Okay, so y equals 0 is one solution. Well, that, yeah, of course, we already know that. Then we have that y squared minus 4 is equal to 0. This gets us down to y squared is equal to 4. So y is equal to plus or minus 2. All right, so this has got to be y equals 2. And they intersect that way because x equals y cubed, or the cubed root of x does continue on down this way. Okay, and the line intersects over here at -2. Okay, so anyway, we have our limits of integration now. Right, so the volume is going to be, let's, what color should I do this in? Let's do it in yellow. Okay, so we're going to get pi from 0 to 2 of the right squared, so that will be 4y all squared minus the left squared. So that'll be y cubed all squared dy. Okay, so let's shift over a little bit and continue this over here. This will be the integral from 0 to 2 of, this will be 16y squared minus y to the 6th. Okay, so we'll get pi. Actually, now I can just integrate. So we'll get 16y cubed over 3 minus 1/7 y to the 7th. Okay, so we will get 16/3 2 cubed minus 1/7 2 to the 7th. All right, and that is not going to come out to be extremely nice. All right, when I checked my calculator, this came out to be something like 512 over 21 times pi, which, you know, at this point, I'm not that concerned about the arithmetic to get there. What's important here is the setup, because it's the setup that gets us where we want to go. Okay, so yeah, if you want to revolve around the y-axis, well, hey, no problem. Okay, you just need to set up your integral in terms of y. All right, I think our best bet at this point is just doing some more examples that kind of go through these possibilities. All right, so the one we're going to start with here is we want to find the volume of the solid generated by revolving the region bounded by y equals e to the x over 2, y equals e to the negative x over 2, x equals ln 2, and x equals ln 3 around the x-axis. Okay, so I want to show you how you can go about doing this without even knowing perfectly what this thing looks like. Okay, so to start with, one, I'm revolving around the x-axis, so I know I'm going to want to set this up in terms of an x integral. Okay, that's not too bad. Now, e to the x, okay, or e to the x over 2, either way, that's a not a parabola, but that's an exponential, so it, you know, does this thing. It blows up pretty fast. But e to the negative x over 2, that's another exponential that decays. Okay, so it looks something like this. Now, ln 2, well, you know, that's some positive value, say it's right here. And ln 3, say, is here. So this is our y equals e to the x over 2. This is our y equals e to the negative x over 2. And remember, the curves y equals some constant, x equals some constant, those are vertical lines. So we are, oh boy, that's so let me adjust this a bit so I actually get an intersection here. There we go. Okay. So what we are doing is revolving this thing okay, around the x-axis. So we are creating a strange curve because the inside that we're hollowing out gets sort of smaller, okay, and the outside gets sort of larger. So we've got some sort of weird thing here. But remember, it doesn't really matter exactly what it looks like. I can still find the volume, because the volume, well, it's just going to be the integral, or pi times the integral, lower limit of x, so that's going to be ln 2, upper limit of x, ln 3. Then it's going to be the top squared. Well, the top is this y equals e to the x over 2, so it'll be e to the x over 2 squared. Then minus, let me make that a better 2, minus our bottom. Well, the bottom curve is e to the negative x over 2, and we'll square that guy too. All right, so then we'll get pi times the integral of ln 2 to ln 3 of, when we square this, so we're going to multiply the exponents, so we'll get e to the x minus e to the negative x. All right, I want to continue this over here. Okay. All right, now to integrate this, no problem. Integral of e to the x is itself. Then integral of e to the negative x, well, that'll be negative e to the negative x, so I'll get plus e to the negative x. And then we're going to evaluate this from ln 2 to ln 3. Now, before I do that, to make this a little easier on ourselves, make this 1 over e to the x. Okay, and the reason we're going to want to do that is because we're plugging in ln stuff. So when we plug in ln 3, well, e to the ln 3, the e and the ln 3 cancel to just give us 3. And we'll do that here on the denominator as well. Okay, so there's our plugging in the ln 3, and then we'll subtract out when we plug in the ln 2. Okay, so we'll get pi times, remember these cancel, that'll be 3 plus a third minus, I'm going to leave my parentheses there, 2 minus a half. All right, so it'll be pi times, we'll have 3 minus 2 plus a third minus a half. All right, so we'll get 1. And then here, it will be 2 minus 3 over 6. So that will be negative 1/6. So pi times 1 minus a sixth. So that should be 5/6 times pi. And there we go. Okay, there's the volume of our funky solid there. All right, so for this example, what we want to do is find the volume of the solid generated by revolving the region between the curves y equals 0, y equals ln x, y equals 2, and x equals 0 around the y-axis. So around the y-axis means we're going to want to set up an integral in terms of y. So let's look at what's going on here. Okay, so the line y equals 0, y equals 0 is just this horizontal line here. Okay, then y equals ln x looks like this. It has a vertical asymptote at 0, and then at 1 it crosses the x-axis, so there's y equals ln x. Then we have y equals 2. So I'm going to put that right here just so I get a good intersection. Let's try that again. Okay, so here's y equals 2. And then x equals 0. Well, x equals 0 is this vertical line here. Okay, so what we're doing is revolving this around the y-axis. Okay, so we've got something that will look kind of like this. Okay, so now, since we're going around the y-axis, we need our integral in terms of y. Well, it turns out that we have the rightmost, but the left is just the axis. So we don't actually have to do right squared minus left squared, but I mean, we could. This would be y equals 0. Okay, I mean, that just, or I'm sorry, x equals 0, right? So x equals 0 would be our left side. And so when we took minus 0 squared, it would just disappear. Okay? So we need to get this guy in terms of x. Well, if y is equal to ln x, that means x is equal to e to the y. You just take, well, the e of both sides, essentially. Okay? So this is our right side. So we have our right side and our left side. Okay, so our volume will be pi times, now it will be the integral from, it's going to be in terms of y, so our limits go from y equals 0 to y equals 2. Then the right side squared, so that would be e to the y squared, minus the left side squared. Well, in this case it's 0. Normally we wouldn't write it, but I do kind of want to just show how it pans out, even if we did. So this would be the right side squared minus the left side squared. All right, so we'll get pi times the integral from 0 to 2 of e to the 2y dy. Okay, and we integrate this. The integral of e to the 2y is 1/2 e to the 2y. And we'll evaluate this from not 0 to 1, but 0 to 2. So we get pi times, it'll be 1/2 e to the 4 minus 1/2 e to the 0. And this is where you got to be careful, because we're so used to, when we plug in the 0, getting nothing. But with e's, we can't do that, right? Because that's going to be 1. So this will be pi times 1/2 e to the 4th minus 1/2. All right, and that'll be our answer. So we could actually factor out a 1/2 to get us pi over 2 times e to the 4th minus 1 if we wanted to, but that's it. Okay, so hopefully that's enough to get you rolling on the homework, and I will catch you all in the next one when we start talking about the not the washer method, but the shell method.